Okay, so for EX11, I asked you to do an exercise based on correlation of wheat prices and disturbances, or riots basically. So to start off with, I asked you to download this file here, so ASC140020, student version of that, and I've already got one version, so I'll just save it again. And I do ask you to rename the file with your initials, so I'll open it up. And I got here to come up here to File, Save As, and I'll save it in the same place as it currently is on my desktop. So EX011, put my initials after JF. And essentially what this is then, we've got the number of disturbances per year. This is taken from Hudson, who in turn took it from Rostow in a major study of this. So we've got the number of disturbances between 1810 and 1821. And then we've got what we're interested in now, which is the wheat prices per quart, in shillings per quart, down here for again 1810 to 1821. We've thankfully got a complete data set. We've also, for reference in column D, here got the business cycle index, which is telling us whether 0 being there being a kind of deep depression and 5 being a major peak in economic activity. So this is an index they've created about kind of economic activity basically. Probably features estimates of GDP, production appropriate for that time period. Obviously our data is not very good for early 1800s in terms of GDP. Okay, so let's get going. What I asked you to do in EX11 is pretty simple, which is to use the correlation function in Excel in order to get an estimate of the strength and direction of the relationship between the two variables. What we can't tell from correlation, as you should have picked up from your reading, is causation. So we can't say which variable is affecting the other. All we can do is get a Pearson correlation coefficient, which tells us it's a value between -1 and 1. 0 would be no relationship, no correlation in any direction. These values don't affect each other or don't move together. A positive correlation, so something coming near to 1, would be that as one value increases, the other's value also increases. And a negative correlation, so downward slope, would be as one value increases, the other tends to decrease. Okay, so values near to -1 would be a strong negative correlation. So that figure allows us to both tell the direction, whether it's positive or negative, and how close they are to 1 or -1 tells us the strength of the relationship between the co-movement, if you like, between the two variables. So in Excel, it's really quite nice and easy. We just go equals, so I'm just doing it in column F here. Correl, so CRREL, and then we open our brackets and we can enter our two arrays. So it takes one array separated by a comma and followed by another array. And in this case, it's just the time series, different time series for our variables. So let's put disturbances in, and then wheat prices as our second array. At the moment, we're not too bothered about whether they're dependent or independent variables, because correlation, as I say, doesn't. The result would be the same either way around, because it's not telling us anything about direction. So press enter, and that looks like we've got a strong positive correlation. So as wheat prices increase, it seems that so do the number of disturbances. Now for EX12, I ask you to take this a stage further and do some basic kind of regression analysis. So the first step in doing this is to do a scatter plot, and and see if we can pick up a relationship between the two variables. Positive might be. It will also confirm for us that we've got a positive correlation here. So the way to do that is in Excel to come up to Insert, and over to Charts here. So we've got different options. And select scatter plot. So it's, because we had our cursor in there, it's trying to plot that for us, which isn't quite what we want. So we'll just come up and reselect it. Okay. Now it's managed to select that again for us. So we can change our data to make sure we're doing these. So we're going to select data. And we'll just remove that for now. And we'll start again and add a new one. So add a new legend, a new series, sorry. So we'll call this wheat prices and number of disturbances. That's going to be our title. Now along the x-axis, so on here, we want our independent variable. So the thing that we think is going to change or alter, cause an alteration in the dependent variable, i.e. the thing that we're interested in, so the number of disturbances. So in our case, our independent variable going along the x-axis, we are going to have wheat prices. So we'll come over and select the column, a cell block that we need for wheat prices. There we are. And for our y value then, our dependent variable, the number of disturbances, we'll come over and select the cells in column B. Okay, press OK. And we'll just do a check that that makes sense. Yeah, we can see they match up the values. Great. So we've got our basic scatter plot. Now, what I'd like you to do and have some practice doing is formatting these charts. So I'm going to come over immediately and add in actually chart element. So we need to put some axis titles in. Let's put the horizontal one in. I'm going to call that wheat price shillings per quart, just to measure a volume. And we'll do the same thing again for the vertical axis. This is the number of disturbances. There we are. Great. Okay, to change the size of the dots here, we could just go format data series, and we've got lots of formatting options that you can play around with as you need to get the best kind of graph you like. Scatter plots you often do have to alter the size of the dot, because if you've got lots of data, obviously you can crowd them out if you have if you're using large dots. Okay, so at the moment we've just got the scatter plot data, and we can kind of see that yes, this is a strong positive correlation. As you get an increase in the wheat price, it seems that you also get a vertical increase in the number of disturbances. But regression takes that stage further by asking how much of the variation in this our dependent variable is explained by increases in our independent variable, i.e. wheat prices. So how much of the increase in disturbance, because it's not kind of perfect, this line, so how much of that increase seems to be due to an increase in wheat prices. So we're kind of getting halfway, if you like, to having a kind of theory about causation from this. Now the general form of a regression equation looks like this. So it looks like y, which is our dependent variable, i.e. on the y-axis, equals a plus b times x, or in algebra we just put x. Okay. Now, a equals, in your mind, if you imagine we're trying, this formula here is for a line, so the formula for every y position, we can know where that how high to place each of these dots, if you like, by having a, by knowing what a is, which is going to be the intercept, so where this kind of line, if you imagine, would hit the the axis, plus a certain number, b, we don't know, a variable, could be anything, 10, 20, whatever, times our x value. So this formula is all about, once we know where something is on the x, so a wheat price, say 80, the purpose of this formula is to tell us how high we have to go up the y-axis to draw our dot, if you like, to get the number of predicted disturbances. Okay, so it's a way, this formula, if we do it for all the points on that we've got for on our x, we end up with all the points for y, and we can kind of draw a line, if you like, about where theoretical points on our x-axis would end up. So we don't have any data for a kind of, what's that, 110. But if we use this formula, we can say where it should be and where we would expect it to be based on other observations. So in Excel, it's quite easy, to get that calculated for you rather than work it out. As I've already said, A is, once we calculated that line, where we would expect our line to cross the intercept here. And B is simply the measure of the slope of this line, if you like. So you can imagine that A could be the same thing, say -1, but we could have some lines or ordinary least squares, best fit trend line, if you like, that tried to go through the middle of all of these. That was kind of one that was sloped like that, one that was very sharp. So they would all have the same intercept, if you like, of the x-axis, but very different slopes. So B is what's going to control that for us. As I said, you don't need to quite have a full understanding of the algebra for that to get Excel to do it for you. And the way to do that quickly is to right-click on your data series, so format data series. You can go through there and do it, but it's easiest just to click Add Trend Line. And this gives us all the options we want. So we want a linear trend line, because that's the ordinary least squares, so it's trying to minimize the squared differences between the mean, as the technical explanation, and each of the results. So it's fitting a line where the differences between the squares of the mean results, and the mean would work. And we can set the intercept if we want, but we're not going to do that. What we need to do, though, to get a regression is to display the equation for us. So this is a version of this based on the data we have, and to display the r squared value, which is going to tell us how good a predictor, if you like, this equation is for our data. So in practice, what do we have here? Well, Excel's given us a nice equation here for y, and it looks slightly different to this, obviously, with the numbers filled in. But because our intercept is a negative number based on the observations here, our line will cross the x-axis at not 0, but minus 28.739, precise, so somewhere down here by the look of it. It's put that in the second half of the equation because it's a minus number, whereas up here we've got a in the first. So this highlighted here, this minus 28.739 is a. Okay, it's just been rearranged because it's a negative number. B times x, so we've got x in there still, and then we've got this 0.7087 times x. Okay, and that simply means that if we have an x value, say 100, to figure out where this line should fit, we would need to times it by 0.7087. Okay, so we can bring the calculator up and do a check on that. So we're saying we want to find out where hypothetically that point is on the line. We could do 100 times 0.7087, because that's the b times x bit. Press enter, and then we could minus off, which turns us to minus 28.739, and we get a value of 42.13. And if we look up, yeah, that's pretty much where that is. Okay, so the formula is just to tell us how far up the y-axis we should be going for every result that we have for x, or for any kind of value that we can plug in for x. Now the r² value is a little bit different. The r² value is telling us that is a percentage, basically. It's telling us that in this case, around 90% of the data is being explained by this line. 90% of the variation. You can see this isn't these dots don't perfectly fit along this line. If they did, this line's formula would be explaining 100% of the variation. Very accurate. Whereas in this case, we're only explaining kind of 90% of the variation. So these bits are all left unexplained. There must be other factors that are causing them in our model, predictive model. Okay, so r² is really important because it tells you how good, if you like, a predictor of the number of disturbances over here on our axis, on our y-axis, sorry. The x-axis is. So how good a predictor weak prices are of the number of disturbances we're likely to see. Alright, I'm rambling a bit, so I think I'll leave it there and move on a separate video to EX13 and descriptive statistics.